And okay, so this question is a bit longer, and some of it's being hidden there, but I'll expand the question so you know when it's being asked. So you stand at the top of a deep well to determine the depth D of the well. So we've got our well, and again we're going to just pretend that's straight. Our well, and there's our water, and we got our little dude standing here, and he drops a rock, and the rock goes all the way down, splashes in the water, and we listen for the splash, which the sound travels up the well. Again, the whole length is D. And so the rock falls initially from rest, so VI equals 0. Its acceleration will be gravity. So it'll be due to gravity, which for these purposes I'm going to use minus 9.8 meters per second squared. And the speed of sound that we're going to use for the sound waves is 342 meters per second. Okay, so we drop the rock and we listen for the sound waves to come back up, and it takes, the full time takes 3.9 seconds. So that's our T total. Okay, and so the first question is just to find the quadratic equation for the distance D in terms of the time, the acceleration due to gravity, and the speed of sound. And it wants us to arrange the equations so that there's no prefactor on the D squared term. So. Which is how we prefer it anyway. So let's start off. So the acceleration is minus g. So this is for the, I'll call it the one leg, and then we'll worry about the two leg afterwards. So the two leg would be the sound leg. So for the first one, the acceleration is minus g, and we're going to use the fact that acceleration is dv by dt, so the derivative of the velocity by time. So that means that dv is a dt, or we can integrate this expression to then get our velocity as a function of time. So if we integrate from v0 up to vt, and in this case we might as well call this first leg t1. So we're going to call the entire thing t1, so I'm just going to integrate it all the way up to t1 dv. And that's going to equal the integral. I'm going to bring the minus sign out front. G from 0 to t1 dt. So now the dv integral is just going to turn into v, evaluated between v0 and v of t1. And that's going to equal minus g. The integral of dt is again just going to be t from 0 to t1. Okay, and I'm just going to bring this up a bit. Okay, so if we do our integration limits here, then we have v t1 minus v0 is equal to, and so when t is 0, the whole thing's going to be 0, so minus g t1. And as the rock starts at rest, right, so the boy's holding the rock at the top of the well, so it's going to be initially at rest, that guy's also 0. So then that means our velocity at t1 is just minus g t1. I realized now that instead of integrating this to t1, because we're looking for the distance, I should have just integrated up to t. So I'm just going to do it as a function of t instead, like this. And I'm going to get rid of the 1s, because we don't need those right now. So ignore the 1s. It doesn't change anything, but just the explanation and the next part of the question. Okay, so I'm just going to leave it as t. So this is now the velocity at any time t during the transit of the rock down the well. The reason why I did that is because, well, now we want to move from velocity to displacement. So our x is, or our velocity is dx by dt. And so then we can get our dx by rearranging this expression and integrating. And so then using this integral, we have integral from of dx from 0 to t, from x0 to x of t is equal to integral minus gt dt from 0 to t. Now we will want to take it from 0 to t1. And now the integral on the left is just going to be x from x0 to x of t1, and that's going to equal minus g, so the integral of t dt, so the power rules are you put it up by 1 and then divide by the power, so it's going to be t squared over 2 from 0 to t1. And then finishing this off, we have x of t1 minus x0 is equal to minus g t1 squared over 2. As this expression is going to go completely to 0 when t equals 0. Now if we take the top of the well as 0, then that's 0. And x of t1 is the depth of our well. But if we are taking the top of the well as 0, then the bottom of the well would actually be minus d, right? As we're moving in a negative direction. So our final distance is actually minus d. So that would be minus d down here, okay? All right, so what we have then is minus d equals minus g t1 squared over 2, or canceling the negatives. Good. Okay. So now we have one expression for the distance d. Okay, and we can solve that for our time as t1 equals 2d over g square root, which is a quantity we will need in a second. So now for our second leg of time, it's just the speed of sound part. So in this case, our velocity is constant, meaning we can express our velocity in our second case as, what do I call it? I call it Vs? Yeah, okay. So in our second case, we can call our velocity distance over time, which is just d over t. In this case, I guess I should do it a bit more, a bit better than that. So in this case, we would call it delta x over delta t, right? So delta x is then 0 minus a minus d, and for delta t, we're just going to call that our t2 time, right? So we're going from the bottom of the well, to the top of the well. So then we're going d over t2. Yeah, okay. Yeah, final minus initial. So the final point is the top of the well, which is 0, and the initial position is at minus d. So it should be a positive d over t2. Okay, so solving this now for our t2, we have d over vs. So now we have our 2 times for our journey, and we know that the total time is 3.9 seconds, and that's going to equal the sum of our 2 times. And so that's this square root 2d over g plus d over v sound. Now, to get our quadratic equation, we could square this right now, but that's going to get messy. So I'm just going to rearrange it as 3.9 seconds minus d over vs equals square root of 2d over g, and I'm going to square this. So if we square that expression, then we would get 3.9 minus d over vs squared is equal to 2d over g, or 2d over g is equal to 15.21 seconds squared minus 7.8 seconds d over vs plus d squared over vs squared. And then just moving this 2d over g inside, we get 0 equals 15.21 seconds squared minus 7.8 seconds over vs plus 2 over g, all multiplied by d, plus d squared over vs squared. And then for our final step, we're just going to multiply through by this vs squared so that there's nothing on the d squared. So then that gives 0 equals 15.21 seconds squared, Vs squared, minus 7.8 seconds, Vs, plus 2 Vs squared over G, D plus D squared. And then that is now that's our quadratic equation, so that's the answer to part A. And then for part B, it just asks to solve the quadratic for D. So to do that, we're just going to plug in values. So for Vs, we're using 342 meters per second. And for G, I'm using 9.8 meters per second squared. So with that, the quadratic comes out to be quite messy, but still doable. 2.44 meters squared minus 26,537.804 meters D plus D squared. And so then using these numbers in the quadratic equation, we have D is equal to minus B, so that's just 26,537.804 meters over 2A, A in this case is just 1, plus or minus square root of this value squared minus 4 times, okay, I'm just going to actually use a new line for this one. This is just going to end up with me running it into the side. And I'm going to use a big square bracket. So minus, and I'm going to get rid of the square root symbol just because it's kind of in the way as well. So I use a big old square bracket, and minus 4 times 1779022.0.44 meters squared. Close the square bracket to the power of 1/2 all over 2. So this is a little messy, but this is just this value squared minus 4 times that value and times 1. So when we work this through a bit, we're going to get 13,268.902 on this side, and plus or minus the square root of 697,138,955.715 meters squared over 2 on that side. And then taking our square root and dividing by 2, we get 13,268.902 meters plus or minus 13,201.695, which means D is either 26,470.597 meters, or D is 67.207 meters. So this, which I would say makes much more sense for the depth of a well, or D equals 67 meters rounded to 2 significant figures. So that makes much more sense, I'd say, for the depth of a well. So I think that's our answer. Okay, so let's check through this. So dropped in a well. T down is 3. By the time it takes for the sound to travel to the person's ear. The distance traveled by the sound wave. Okay, so they're solving for the sound wave first. And then, so this is the the distance expression that we solve for before. So this is, okay, so plugging in the T down part, okay. Okay. So the signs, but I don't think the signs matter, so that's okay. Okay, so if we now check our quadratic equation here, so it'd just be d squared minus 7.8 times our v sound plus 2v sound squared over g, so yeah, that's in there, and then plus 15.21 times our v sound squared. Yeah, so that's exactly the same quadratic expression. And then, so now here's our quadratic equation, which again, they've got everything in there the same. Mine's a bit messier, but it's okay. And so it might be just rounding. I don't know where that value comes from actually. So 2.54 times 10 to the 4 looks like it's probably a mistake, since from my calculator anyway, 15.2 times, oh, they're using 334 meters per second. Okay, so they're using 334 meters per second. The question says 342, so their solution is the likely correct, but for the wrong speed of sound. So I'd say the method is correct. Speed of sound in question is 342 meters per second, not 334 meters per second. But the math is correct, and all the the math is correct. It's just the speed they use is incorrect.